Hello, everyone. Welcome to the Introduction to Quantum Computing workshop. Here we're going to explore what exactly quantum computing is and what this field entails for the future. We hope to help you prepare with the fundamentals so that you have a solid foundation laid on through which you can go ahead and start exploring yourself and building on it further.
Hello everyone, my name is Alberto and I currently I study my master's degree in computer science. This is about quantum algorithms for generate fourth morphologic algorithms for binary image, and it's all for my part.
Hi, my name is Leah and I'm a computer science PhD student at the University of Oxford, and I'm also a CUhackit advocate. My PhD research is probably going to be related to quantum compilation and quantum computer architecture.
Hello, everyone. My name is Sanskriti Ranjan. I'm a computer engineering student here at Clemson University. And this summer, I was involved in learning about quantum computing through the IBM QuizKit team.
And if anyone is interested about more about quantum computing, if you are interested, you can follow us in our community, which name is People Interested in Quantum Universal Education, and this is the Discord channel.
So the community that Alberto just mentioned, it's community. So anyone can join, and it's for learning materials, and anyone can join to learn about quantum science and quantum computing, but it also develops learning materials. And so if you'd like to help with developing community-driven open source and accessible quantum education materials, anyone can contribute and help make them more accessible and get a free t-shirt. And the website with our learning materials is at fullstackquantumcomputation.tech.
What is quantum computing? Everybody knows that the information processing systems are based on classical physics, but it is a subset of quantum mechanics, which aims to understand the nature. In other words, the quantum computer helps to model some unsolved problems of the nature, because in classical computing they are complex or even impossible problems. This is possible following the principles of quantum mechanics, for example, superposition and entanglement.
To give an overview of what quantum computing as a field looks like today and what it might look like in the coming years, here in the bottom left, it says systems today. And so quantum computers today have not that many qubits and have a lot of noise, so called gate area in this diagram. And we actually suspect that we're now in the purple area since this diagram about a year ago, where the purple area represents quantum supremacy. This means that quantum computers have now, as of an experiment done almost a year ago by Google and the University of California Santa Barbara's quantum computers are now able to have an advantage in calculating something compared to a classical computer simulating that same computation. In the near future, this gray area is what we'll be converging on, and this gray area is suspected to be when VQE, a quantum algorithm, will be viable. And VQE has applications for quantum chemistry, so we think quantum chemistry will be the first usage of useful quantum computation. About 10 years from now, we suspect that the green hashed area in the top, where it says sure, would be useful on a quantum computer such that it could change how our cryptography works. So actually the US government is currently running a competition of sorts to see what kind of cryptography schemes we can have to replace our current cryptography. And the blue dotted line says classical simulation. So that's kind of the limit that we suspect the best supercomputers that we have today would be able to simulate of quantum computers. So we do predict that in the coming years, quantum computers will be able to do calculations that classical computers would have no shot at. To dive under the hood of what a quantum computer looks like underneath, in the 1950s, a classical computer, so say your cell phones and laptops and whatever you use, those looked pretty bare bones. But those computers today have now evolved to have so many different layers. And quantum computers today are really basic in that they are analogous to what classical computers were like in the 50s. So all those layers between quantum hardware and to the quantum algorithms that we want to eventually run on quantum computers, in between there's a lot of questions as how to make all this efficient and well-behaved and all that other good stuff. But most people who are using quantum computers will not need to know how they work underneath, and just like that, that's kind of like how most people who use computers today don't build computers from scratch or anything like that. So this is just a cute image that shows in the kind of more towards the beginning, computer scientists, physicists, engineers, and mathematicians will have a role to play in building quantum computers. But in the using of quantum computers, there's going to be a lot of fields involved, so it's really, really interdisciplinary. For example, applications of quantum computing include aerospace, chemistry, cryptography, environmental science, natural language processing, pharmaceuticals, supply chain logistics, robotics, and finance, and there's a lot more. So because there's so many areas, there's no one-size-fits-all approach to learning about quantum information science. And by the end of this presentation, we'll show you about, and actually you can program a quantum computer from your own device and run your code remotely on a quantum computer. We'll start with the really basic, most basic element of a quantum computer, which is called a qubit. It's short for a quantum bit, where a bit is like a 0 or 1 for a classical computer, and a quantum bit can have the values of 0 or 1, but it can also be in a superposition of those values. So it can have some probability of being 0 or 1, but there's a bit more physics underlying that. Here is a box. So the cats on the previous slide have the state of either alive or dead, and if you stuck them into a box where you can't see inside, I guess you can't prove whether there is a living or dead cat inside in this thought experiment called Schrodinger's cat. And so if you open the box, that would be analogous to a measurement of your qubit, where the cat is either in the alive state or the dead state. But while the cat's in the box, let's say that you put some death oracle along with it, so like say a bomb, then if you were to open the box, the normal way is analogous to opening and to measuring your qubit in the 0-1 basis, and then you would see either the state 0 or 1, which in our analogy is either alive or dead. But if you were to, here's where the quantum part comes in. If you were to rotate the box, this analogy being to measure in a different basis than the computational or 0-1 basis, in this case, this basis is rotated halfway between 0 and 1, so the plus state is halfway between 0 and 1, and then the minus state is just orthogonal to the plus state in this unit circle representation. Well, if you were to now cut open the box, you can change the state of the qubit. So if you were to cut the fuse to a bomb that otherwise would have killed the cat, or if you were to decapitate the cat, then you would be possibly changing the state of the cat, whether the cat's alive or dead.
What is a qubit? Remember in the classical computing that works with a bit? The bit has two possibilities, the value 0 or the value 1. But in the qubit or quantum bit, we can work with a vector with two dimensions, the state 0 or the state 1. This is what every state corresponds with a scalar value. That value represented the amplitude of the qubit in a specific state. We can visualization with the Bloch sphere. In this case, the possibility of the state 0 is with respect to the axis S, and the top is the state 0 and the down is the 1, 0. We can rewrite this one with a vector of two dimensions. Previously, we mentioned the Hadron method of the positive and negative states or bases. We can identify in the axis X in the Bloch sphere. And another remark, multiple qubits, for example, the state of the C qubit or states 1, 2 is equals at a product, a tensor product of these values, and 10 is not is impossible to represent a multiple qubits. Multiple qubits, it can represent it like a concatenate. We need to is the result of the product tensor between two qubits and the respective states. Qubit or quantum bit versus classical bit or bit. The most important and amazing thing is the n qubit is equal to representing 2 to the n bits. Another is we can obtain different values when I superposition the initial or the inputs of the qubits and it applied the corresponding gains or in the quantum circuit we obtain in the measurement different values. This depends of the probabilities to obtain with the scalar finally state, and we need to apply the absolute value with the power of 2 in the scalar and we obtain the probability to obtain that value. If we repeat the measure n times, we can represent the probability in another way. Following with this idea, we need to identify in the quantum circuit or is built up with qubits and quantum gains. The qubits is the quantum gains we can represent it with a matrix, the size n by n. We apply the dagger or the transform conjugate, we obtain the identity. These gates or quantum gates transform the value and the probability of state of initial quantum bits for another finally or output quantum bits. It is possible with the measurement when we collapse it with the outcomes with the representing the value gates.
Now that we've learned about quantum entanglement, we're ready to learn about our first quantum computing algorithm. This is called the Deutsch-Jozsa quantum algorithm, and although it's not super useful in real life, it'll give us some insight into what a quantum algorithm is, and we can come up with a scenario in which it could be applied. So in this toy scenario, let's just say that all the world's cats become overpopulated, and then due to too much competition for resources, all but M of them die off, which is a situation you might have heard of in high school ecology. Being the scientist you are, you concoct a magic function f you hope to apply on all the world's cats, whether they're dead or alive, so that exactly half of them are alive in the end. Well, how such a function f would work in real life, no one knows, but let's just say we can treat it like a black box, so we can use it without knowing how it works. In computer science, such a function, like a black box, we call an oracle. Just noting there's no procedure to bring dead cats back to life using quantum mechanics, but there's some very trippy concepts like quantum teleportation, which has been done in experiments before, and time travel, which some models of quantum physics suggest is theoretically possible. Also, for the sake of this quantum algorithm, this is the balanced case, but for the sake of the analogy with the cat, so let's just call this a success case. The problem is you think that there's half a chance in this scenario that when you concocted f, you messed up real bad. And if you truly did mess up, all the cats in existence would have the same state after f. Either all the cats will end up dead or they'll all end up alive, and then you're back to square one with the overpopulation problem. And the government you answer to doesn't take chances. You need to test your function before they let you anywhere near piles and piles of cat corpses. For the sake of the algorithm, this is the constant case, and in the analogy, this is a failure case. To test your function, you could perform your procedure on cat after cat and pray you haven't been real unlucky. But that's too much work and you'd rather just do it once. You have better things to do than spend all your time with cat corpses. So you make the quantum version of f so that you can just run it once. That's an exponential speedup of the quantum algorithm over the best possible classical algorithm. Here's what that quantum circuit looks like. So the quantum version of f, as said before, it's u sub f in this slide. So it's a unitary gate that implements f. Well, how the quantum circuit looks like, you have n plus 1 qubits, where n is how you represent the data of the cat, so all the information of the cat, in n qubits. How many qubits that is for a real cat, I have no clue. But if you had 300 qubits, so n equals 300, you could simulate all of the particles in the known universe. Well, first you apply the Hadamard gate, which we've already learned about, to the n plus 1 qubits. Then you apply u sub f. Then you apply Hadamard gates to all of the n qubits, and then you measure the n qubits that represent the state of the cat. And how the Deutsch-Jozsa quantum algorithm works is that if you get a measurement outcome on the n qubits of all zeros, you have the constant case in which the function f is constant, has constant outputs. So that's a failure case in our scenario. And if you measure anything else, you've got the balanced scenario, which means that in our cat analogy, you succeeded with your function f. The easiest way to use a quantum computer is, in my opinion, the IBM Quantum Experience, because you can drag and drop circuits, gates for the circuits in browser at this link here, and you can run these circuits on quantum computers, real quantum computers all around the world over the cloud. How it looks like, the interface is here. So here you can see a bunch of gates that you can drag and drop into the circuits, which are the lines that are labeled Q0, Q1, Q2, and C3 here. Although you can change the number of qubits and the number of classical bits that you measure to. But here we don't have any gates in this circuit. And you also see the measurement probabilities that are what you would measure for each qubit if you were to measure it currently. Currently there's no circuit, so you would just trivially measure zeros. And here's a Q-sphere. So a Q-sphere is a new thing that recently added to IBM Quantum Experience, where you can visualize the state of your quantum system, in this case, all zeros. By the way, this is free for anyone to sign up to, and you can run on a few quantum hardware, so a few quantum computers, just with the free version. And here's a code mode, so if you want to move beyond the graphic mode on the previous slide, you can also download CUhackit, which is IBM's quantum programming language, and it's really easy to get started with. There's a CUhackit textbook, and there's a video series, and we'll also cover how to install CUhackit later in this slide, or in this presentation. Back to our cat analogy for the Deutsch-Jozsa quantum algorithm. What does u sub f look like in the balanced case, also known as the successful case in our analogy? So between the dashed lines here, we have two CNOT gates, and these two CNOT gates happen to implement the u sub f for the Deutsch-Jozsa algorithm for n equals 2. So if somehow we could represent our cat with just 2 qubits. In this case, the measurement probabilities yield zeros for the input when your input qubits are all zeros. And so we can show that this is the balanced case of the Deutsch-Jozsa algorithm by showing if your input qubits are both in the 0 state, then your output qubit will, then the function output will measure as 0. If one of the input qubits is in the 1 state and the other in the 0 state, then your output of the function f will be 1. And if their inputs are both the 1 state, then the output will be the 0 state, as shown with the measurements on the previous slide. And here's what the quantum circuit looks like again, and just to prove it works for the constant case as well. So when u sub f for n equals 2 has no circuit, then the measurement is all zeros, as shown with the measurement probabilities here. And when you implement the Deutsch-Jozsa algorithm for the balanced in the successful case for our analogy, then you measure something that's not 0. So you can see here our measurement result is a 0 and a 1 for the 2 qubits that are measured. And so that's a successful case. So you successfully learned how to keep half the world's cats that were dead or alive and solve their problem.
After seeing the probabilities of the qubit, we need to ask us how can we modify the qubit. We can answer with the next example. First of all, we consider the last qubit as the initial step or our qubit example, and we can rewrite it in a vector of 2 dimensions, 1 and 0. Secondly, we need to identify a quantum gate. For this example, is the NOT or Pauli X gate. This is a matrix is equal to a matrix to size 2 by 2. We need to apply that, and the result is the dead hidden state. Another example, and one of the most incredible phenomena of quantum computing, is to generate the superposition of the 2 hidden. This is possible by using the Hadamard gate or H gate for its symbols. This composed in a matrix of size 2 by 2, which values 1/2 of the square root, both positive and the last negative value. We need to apply it with the same last hidden state or 1-0 vector of 2 dimensions. The result of this operation is the linear combination of the 2 hiddens, the sum of the last hidden with the dead hidden, held h on the square root of 2. The measurement is the last part of the quantum circuit or quantum algorithms. This is very important because with this we can look the probability of then one specific state. In this example, we can 2 hiddens in a linear combination. When I apply the absolute value by power of 2, we can identify the probability of these hiddens. 1/3 for the last hidden and 2/3 for the dead hidden state. Quantum entanglement. This is our first quantum circuit for identifying an expected result. First of all, we needed 2 different qubits, Alice cat and Bot cat. After that, we need to apply the Hadamard gate for the previous slide. And another important gate, this is for side 4 by 4, and this is the C-not gate or not controlled gate. And the result of this one is the linear combination of the 2 values or entanglement values of the hiddens between Alice and Bot cat.
Alright, so now let's proceed with understanding how we would go about implementing our CUhackit code on IBM's quantum computers. So firstly, what you would have to ensure is that you have Python 3.5 or higher installed, and CUhackit is possible to be installed in either of these 64-bit systems. So you would then go about installing CUhackit with this command. So as you can see, that generates a couple of messages and you have already installed CUhackit. Next, what you would do is, in case you do not have Jupyter Notebooks installed, you would have to implement this command, and that is how you would be able to install Jupyter Notebooks. If it has already been successfully installed, you will see this message, and then we could proceed with understanding if everything has been correctly installed, and we would then call upon the module to ensure that we are proceeding on the right track. So since it does not return any error, it means that we have CUhackit installed over here. So let's understand the three components that are required to create any of our quantum circuits. You could either use just the core qubits or the quantum register inputs, or you could have the classical register, which would basically be the number of qubits to be measured from the quantum circuit. Or we could create our own quantum circuit by applying different quantum gates to the qubits. So let's proceed with the first basic example, which is basically calling a qubit in its 0 state and then measuring it, which we would proceed by implementing this command. So you're basically calling a qubit here, and you're storing it in QR. You are then calling upon a classical bit, and then you're then measuring basically this using qubit.quantum circuit, and you're storing its value in program. So here we have implemented a basic quantum circuit, and we will then be measuring the value of the qubit over here. So let's implement this. And that is basically how you can go about implementing a basic quantum circuit. So if we wanted to visualize this quantum circuit, this is how we would implement that. And you can basically see here's your qubit, here's the output, and this is basically basic quantum circuit. So if you wanted to get a better idea of this and simulate it, this is the command we would like to implement. And as you can see over here, now you have a better visualization of Q1, our qubit, being implemented in the quantum circuit. So this entire simulation process is performed using a backend. And over here we have to select a backend, and over here we have selected QSM simulator, which you can go about doing using this command. Now, if we wanted to print the values that we got here on this measurement, on this quantum circuit, this is the print statement that we would use, and we would then be able to get this command. Let's now proceed to implement this basic quantum circuit on a histogram, and we can actually visualize and see how the qubit 1 state, what state it basically is in. So if we implement this command right here, we would see that our qubit is in state 0, and that's basically the entire probability. There's no other state that it can be in currently. So quantum computers that we are trying to run over here, we would have to first create an account at this link, quantumcomputingibm.com. And once you've created your account there, you would have to proceed to the section which says My Account, and you can save the token that you would need to use a real quantum computer. It is easier if you save that account in your local computer, because then you can just implement it for future implementations of QUHACKIT code. Otherwise, you would have to keep writing that token again and again. So to save that account, this is basically how you would go about proceeding it. You would replace my token with whatever your token is. I will just leave it at that over here right now because I've already done that, so I would not like to override that. Once you have saved your account, you can then load that token using these commands. So you basically load your account onto the IBM Quantum computers, and you then select a provider that you would need. You can then go ahead and select a backend. In this case, IBM Q16 Melbourne is selected, which would help you to select the quantum computer you would like to use. And if you implement this, you would then see that you are able to execute it on your platform. Next, if we wanted to check the result that we actually got on executing our quantum circuit on a quantum computer, this is the command we would express, and this is the output we would receive, that our 0 state has this value and our 1 state has this value, basically the counts. And we can then go ahead and plot this on a histogram. So now you would see that your qubit actually exists in a 0 state as well as a 1 state, and these are its probabilities that it exists in. So now let's see how we would go about implementing a single qubit using the state vector method. So in the state vector method, we are basically indicating the state of a qubit, and then we're going about implementing it. So here we have implemented state 0, and we are storing that in SV. We have gone ahead and implemented it. Now we can see that it is 0 when we type in sv.data, because we can see that the array consists of 1 plus 0j and then 0, which is basically state 0 of the qubit. To visualize this on a QSphere, we can implement these commands, and you can see that on the QSphere it exists only in 0 state. If we were to apply an X gate or a NOT gate, this is how we would proceed. And remember that the X gate is called a NOT gate because it changes the basis of 0 and 1 changes 0 to 1 and 1 to 0. So it basically flips the bit value of the qubit. So suppose over here we have a circuit which is defined using this command, and we are applying an X gate to our qubit 0. We then go about drawing it, so this is what you would receive. And if you wanted to plot this on a QSphere, these are the commands you would implement. So now we can see that our qubit has flipped from a state 0 to state 1. If we were to apply a Hadamard gate to our quantum circuit and show what quantum state it represents in the QSphere, this is how we would proceed. Basically, we would first create our quantum circuit. We would then apply a Hadamard gate to our qubit 0, and we can then again plot it on the QSphere, and you can see how it is implemented. In the case of multiple qubits, where we can perform quantum entanglement as was explained by Alberto, we can entangle 2 qubits by applying the Hadamard gate and then the controlled X gate or the controlled NOT gate. So to implement this, you would basically create your state vector first, and then you can go ahead and plot that on the QSphere. So now you have your state vector, initial state vector. You would then create the quantum circuit where you would then apply the Hadamard gate, and then you would apply the controlled X gate on it. So applying Hadamard gate on just the state 0, and then you're applying the the controlled X gate on both the qubits. And you can then see that it creates this on the QSphere. So this was the basic implementation of a simple quantum circuits. I hope that was helpful, and please go ahead and start experimenting on the IBM quantum computers. There's so much that you can do and play around with it, so feel free to explore. Thank you.
We can wrap up by giving an overview of teaching yourself quantum computing. Yes, we are in a pandemic. However, the observation that there's numerous challenges to learning quantum information science in a university setting isn't recent. Here's a screenshot from the US government's National Strategic Overview for Quantum Information Science from 2018. The quote I'll read is, "America's current educational system typically focuses on discrete disciplinary tracks, so majors, rarely emphasizing cross-disciplinary study that equips graduates for complex modern questions and challenges, prominently including quantum information science." In other words, because quantum computing and quantum science is so interdisciplinary, it's really challenging to teach and learn at universities. Instead, how you can start learning about quantum computing even before universities adjust, which I think will take many years until we have quantum majors and minors, is through open access online learning. You can just learn a lot regardless of your background. And I think it's uniquely suited to quantum computing education because of this interdisciplinary nature. So you can choose to explore the topics that you want to explore. And of course, open access learning has exploded in popularity in recent years. Well, who benefits from open access learning? 62% of the world has access to internet, so that's really good news that so many people can benefit from making and helping make more accessible resources online. I like to think of the process of creating educational materials as a cycle with 4 parts. So to learn, well, first cover that. I also like to think of learning as having 3 parts to it. So I've just talked about the technical part of learning, but I believe that learning cannot happen without professional and social aspects as well. So with a community along with your own learning, that can act as both a support group and a resource for learning about better ways to learn things. In the screenshot of a post on the website that we're building for open source education resources for quantum information science, Claudia, the author of this post, shared her learning experience from massively open online courses, or MOOCs. I categorize this as social because this post itself doesn't teach about quantum computing, but it's still extremely valuable because it directly links online courses that are free that Claudia recommends and has taken and how to take advantage of them. And here's a screenshot of our post on their website where we have a 2-hour video, over 2 hours, plus a written question and answers. That's the recording of a workshop 4 of us ran on applying to graduate programs internationally. So including myself and Alberto here. We ran this because there's a lot more to the application process than just the application itself. For freshmen, that's like a lot of years away if you're applying to grad schools. But this YouTube video is just free and informational, and we regularly get messages and questions from people who watch this video. After learning, the steps can be to create learning materials and to help curate them, which is making them more accessible, beginner-friendly, and viewable and understandable by a wider audience. This is just a screenshot of our steps for contributing and curating a new learning material, which anyone can submit to. So examples you can learn from on our site include a quantum variant of the Connect 4 game, intro articles to quantum and post-quantum cryptography, and intro code tutorials in 5 quantum programming languages from Alberto. And this is a tentative draft design of the teacher that you would get for free if you helped contribute or curate to the materials. We're actually also learning for beginners to help make the materials more accessible because a beginner knows more than anyone else what kind of challenges a beginner would have in understanding learning materials. And oh yeah, this is a draft because we've just handed off the design to a professional t-shirt graphic designer. The little drawings here are all drawn by people on our Discord server, and they represent 9 different quantum hardwares, so 9 different ways of implementing qubits for a quantum computer. Lastly is the sharing part of this learning cycle, and what that means is if there's a lot of educational materials out there, which there aren't for quantum information science, that's why we're actively making new materials, it needs to go from where the materials are to where people can learn from it. So that's what the sharing comes in, where the sharing comes in. I'm personally in, I think, 13 quantum-related Discord servers. So by finding communities in this pandemic, the communities would be online, you can learn together with, you can ask questions to, seek advice, study together, etc. There's a lot that you can do that can really just, I guess, contribute a lot to your experience self-learning or just learning quantum information science. Lastly, I'll show these logos. So on the very left is the logo of the Unitary Fund, which is a nonprofit, and they have 2 halves. One half is open source software research, and the other half is they take in money from places like Google, IBM, and Microsoft, and many other companies, and they fund grants for different projects that individuals or teams or organizations are working on for open source quantum education and quantum software. The middle logo is the logo for the people interested in quantum universal education Discord server, and some of the people in the server are working on making open source quantum education resources at the fullstackquantumcomputation.tech website. It's funded by the nonprofit the Unitary Funds grant, and the Discord server is open to anyone to join. So there's a few hundred people, from high schoolers to researchers in the field of quantum information science, such that as long as anyone wants to learn, that's a good place to have just a safe space online for people to ask questions, to seek advice, to go to events together, etc. And lastly, on the right-hand side is the Quantum Computing Knowledge Club out of a university in India, but we're hosting online events for anyone who wants to register to attend. It's spearheaded by one of the admins of the Quantum Universal Education Discord server. And that Discord server's join link was given at the start of this talk. So thank you so much for listening to this presentation, and I hope this has given a lot of context and just given you an idea of just ways for students to get involved in learning about quantum information science. Good luck with your hackathon!